Electromagnetics Poisson's equation. Now we apply these Poisson's equations we learned in the video 1. I suggest you go to the video 1 and review before you get into this video. So we consider relative permittivity is epsilon 1 and epsilon 2, and we have external electric field. So what's happened is at this boundary there's some charge accumulated. So the question is how much charge is accumulated around this boundary. So obviously this is going to be P against the E. Okay. For magnetic material, it's the same thing. Relative permeability, which is MS, and this is going to be mu1 and mu2. So it's exactly the same way. Instead of P, it's going to be magnetization. And for magnet case, even without H outside, permanent magnet have this. So we can solve that case. Okay, so Poisson's equation here is there's no true charge around. These are not true charge. Okay, that means it's a pair and total amount is 0. So Poisson's equation become very simple, and this is polar coordinate differentiation. Okay, so how we solve this? Solving this second derivative equation is not that easy. So what we do is, by trial and error, we know the potential equation, phi 1 for inside and phi 2 for outside, and we have just this constant we don't know, and the cos theta is this theta, and this point, this is phi 2. If it's inside, it's phi 1. Okay, so what we do is we take a derivatives and determine A, B, and C, D, and that's going to be the solution for this differential equation for this boundary condition. Now boundary condition is potential energy at the boundary is continuous. So phi 1 and phi 2 should be equal. It has to be the continuous. Orthogonal component of the electric flux is continuous. That means derivative of phi 1 and derivative of phi 2 are also equal. And far away from the sphere, this is going to be external, and that's going to determine coefficient B here. Okay, so external is going to be the B. Okay, so from condition 1, potential is same. We set this means R equals R and phi 1 equals phi 2, and from the boundary condition 2, we take a derivative first, and we set this, so we get this. So we solve for the remaining parameter. Okay, so we get the potential function is outside and the inside, and they connect at the boundary. Okay, so the electric field inside the dielectric sphere is this, which in turn so this part is a contribution from the P. So P is this way. Once we know the P, we know the charge, because Poisson's equation will give. Now let's see, we have a cavity. The relative permittivity is 1 inside. So the electric field flow like that. It's going to flow more inside cavity. So we set this value, then solve this. So we go through this. You can take time to go through the details. We get this. So we replace whole cavity by single dipole. Okay. So this is a single dipole. The assuming polarization is uniform within the circle. We simply integrate by the volume, and using this single bipole P at the center, we can tell this charge accumulated on the surface, which is divided by 4 pi r square. So that's the answer. In case of magnetic, we replace mu2 to this, and epsilon 2 to mu2, and epsilon 1 to mu1. So by using relative permeability this time, exactly same equation. The difference is we change P to M, E to H, so on so. So the permanent magnet, the accumulated these are the permanent magnet charge, magnetic charge is going to create this kind of magnetic field, right? So from this contribution magnetic M, we can calculate what kind of magnetic charge exists on the surface. Okay, so there's two cases, two examples, using the single solution for general case, the two different relative permittivity or permeability. For the sphere, we calculated this. This calculation is quite involved. It's, I don't think you can find it in anywhere else. This is only for this video class. You can get all the answers. So I hope you enjoyed this video. Please check other videos. Definitely you have to check one before you get to this point, because you need to understand the Poisson's equation to understand this example. Okay, and if you like, subscribe.